The objective of this study is the investigation of optical properties and the influence of the polarization and the temperature on heterojunction organic solar cell. Energy harvesting from sunlight is important for saving fossil fuels, which are found to be in a limited quantity in the universe. Photovoltaic devices transforming light into electricity are presently fabricated by semiconductors. However, the main disadvantage of these semiconductor photovoltaic devices is the cost, where their price-efficiency combination cannot compete with the organic photovoltaic appear to be a good alternative for reducing the cost of photovoltaic devices, since they are uniquely cheap. Moreover, they offer other advantages such as environment-friendly manufacturing methods on large area, lightweight, and flexibility. The progresses of organic photovoltaic were widely dictated to improve the power conversion efficiency. In this light, poly has been particularly studied due to its high mobility values and optical absorption coefficient in the visible spectra. At the same time, the electrical properties of polymer layers are significantly affected by the fabrication process, the device structure, and the measurement method. So, of the methodology, we have extracted several P3HT electrical parameters using experimental data obtained directly from a polymeric solar cell fabricated with this material. We have chosen the P3HT PCBM heterojunction configuration in order to characterize the electrical properties of the device. We have fitted the dark current density voltage measurements at different temperature using one diode equivalent circuit. We have determined some physical parameters of P3HT PCBM and the P3HT PCBM, such as optical absorption coefficient, optical band gap, Urbash energy, mobility, and beta coefficient. Precision glass and optic GmbH ETO coated glass substrated were cleaned in an ultrasonic bath, subsequently with acetone, detergent, deionized water, and isopropyl. 40 nanometer thick P.PSS from Bayer by Tronco was spin coated onto the ETO substrate and cured for 15 minutes in 120 degrees Celsius oven. After UV ozone cleaning for 10 minutes, the photoactive layer was deposited as a 200 nanometer thick layer by spin coating from a P3HT, a PCBM solution. The PCBM and the P3HT were utilized without additional purification. Thermal evaporation was used to deposit a 120 nanometer thick aluminum top electrode over the active layer. At the pressure around 2 multiplied by 10 to the -6 torr. The measurements of the optical measurements were performed using a conventional UV visible spectrometer. The measurements were carried out in the wavelength window between 200 and 2200 nanometer. The current density voltage characteristic of these devices were measured at different temperature, and the solar cell was inserted into a cryostat under vacuum to change temperature from 80 to 300 Kelvin. From the transmission spectrum of the layer P3HT, PCBM, P3HT-PCBM can be calculated absorption coefficient alpha of the spectrum and extinction coefficient K of the material. Figure A shows the change of the absorption coefficient as a function of the wavelength of single layers of P3HT PCBM and the P3HT PCBM composites. For the P3HT and close to the absorption edge, alpha was found to be around 3.3 multiplied by 10 power 5 centimeter minus 1, which remains high even upon PCBM addition. It decreases from 3.3 multiplied by 10 power 5 to 1.5 multiplied by 10 power 5 centimeter minus 1. This decrease upon PCBM addition should not have an impact on the performance of the OPV cell, considering the thickness of the layer involved. To study more precisely the optical properties of our sample, we estimate the allowed transition energy using TOC formula. And a gap for the P3HT, energy gap is found to be 1.96 electron volts, which is in line with the values previously reported. Upon PCBM addition, energy gap decreases slightly from 1.96 to 1.9 electron volts due to the insertion of PCBM. The composite P3HT PCBM absorbs less in the visible region, which allows concluding that the P3HT acts as an absorber. It should be noted that close to the absorption edge, the absorption coefficient exhibits an exponential change as a function of wavelength. This exponential tile is associated with the Urbach energy, and it is related to the disorder within the material due to the existence of an exponential distribution of defects in the band near the band edges. The deduced Urbach energy values were found to be 0.08 and 0.54 electron volts for P3HT and PCBM, respectively. On the other hand, the Urbach energy for the composite P3HT PCBM was 0.22 electron volts. The addition of PCBM and P3HT is due to the increase of disorder of the P3HT Borg structure, which decrease into the absorption of the composite layer. In order to extract the electrical parameters, we have used the LNG versus V curves recorded at different temperatures. This gives detailed information on the charge transport mechanism, which will help us in our calculation. As can be observed, the shape of curves depend correspondingly to atomic, depend significantly on temperature and BS voltage ranges. At low voltage, the slopes of the LNG V plots are approximately unity, corresponding to ohmic conduction, while at high voltage, the slopes are greater than 2, corresponding to the space charge limited conductivity region, controlled by the exponential distribution of traps. The device's rectifiing GV behavior is consistent with the conventional thermionic emission hypothesis for conduction across the junction. Using this approach to data, the GV characteristics can be expressed using the following formula equation, where G0 represents the reverse saturation current density and is the ideality factor Kb is the Boltzmann constant and Q represents the electrical charge. We know that G0 can be expressed as this equation. The barrier height is represented by phi b, while the Richardson constant is represented by A et al. The extrapolation of the curve to current axis gives rise to the G0 values, and the slope allows us to calculate the ideality factor. The potential barrier height may be derived from equation 2. Using these values of G0 and the ideality factor, as shown in this table, from the result obtained, it can be that seen that the temperature has been influenced on the electrical properties by the decrease of the properties of compound P3HT-PCBM. To summarize, we have obtained some essential electrical parameters of the organic layer from the analysis of the dark current voltage characteristics of P3HT-PCBM solar cells. Using the current voltage characteristics, we have determined the ideality factor, mobility, potential barrier, coefficient beta. Finally, this study will be useful to understand the electrical properties of P3HT-PCBM based organic solar cells. Thank you for your attention.